Right, guys, I hope you are able to hear me. Amruta, Anbarasi, Andrew, Dinesh, Sai Rakshana, Ivan, Saravanan, Yuvan. If you are able to hear me, make sure your video is on. We'll start the class now. Right, guys, I hope you are able to hear me. Amruta, Anbarasi, Andrew, Dinesh, Sai Rakshana, Ivan, Saravanan, Yuvan. If you are able to hear me, make sure your video is on. We'll start the class now. Right, guys, I hope you are able to hear me. Andrew, Dinesh, Sai Rakshana, Ivan. If you are able to hear me, make sure the video is on or class on. Rohit, am I audible to you? Rohit, respond if you are able to hear me. Andrew, what about you? You are able to hear me? Say a yes.
Yes, sir.
Ananya, what about you? You are able to hear me?
Sir, your voice is very feeble, sir.
Okay. Dinesh and Yuvan, you are able to hear me?
Yes, sir.
Yes, sir.
Okay. Rohit, I did not hear from you. You are able to hear me, Rohit? Check your mic, Rohit. I am unable to hear you. Right. Fine.
Sir, you have unmuted, but you can't hear me.
Okay, fine, Rohit. Let us start the class now. We are already late of the time because today we have to cover three small chapters, but let us see how much we are able to cover. Magnetism and matter, electromagnetic induction, and alternating current. Three simple small chapters from where the questions are going to come in the board examination of approximately 12 to 15 marks. So out of 70 marks, around 10 to 12 marks, maybe 15 sometimes, depends, comes from these three chapters. Today's chapter, scoring chapters, because they are simple, easy to understand, questions are limited, you will have less chance of losing mark. So make sure that you understand all these things today, because in this week, whatever test you write, not this week, I think next week, what test you write will be based upon whatever I'm going to teach today. That is electromagnetic induction, alternating current, and magnetism and matter. Let us start the class now. So first we will start with magnetism and matter. Okay. So this chapter has three parts, if you remember that. Sorry, two parts. One part talks about the magnetic properties. That is, if you have a naturally occurring magnet, what are its properties? We talk about that in the first part. Second part of the chapter talks about the magnetic materials, that is paramagnetic, diamagnetic, and ferromagnetic materials. First part of chapter talks about the what is magnetic dipole, how it is formed, what is the magnetic moment, what is the magnetic field produced by a magnetic dipole, all these things are there. So let us start the class with the basic understanding of the properties of magnet. So you must know, if there is a bar magnet, it has some basic properties. If I ask you, what are the basic properties of a bar magnet? What is the answer? Anybody who knows that? What are the basic properties of a magnet? If I'm talking about magnet, I'm talking about bar magnet now. What are its basic properties? Any idea? Loudly? Yes, what is that called as? Attractive and repulsive property. First property is called as, I can write as attractive property. It can also be referred to as repulsive property, which says that like poles will repel each other, unlike poles will attract each other. So first property of the magnet is called as its attractive property. Actually, before attractive property itself, you have another property called as directive property. Have you heard about directive property? Directive property of a magnet says that whenever a magnet is hanging, it will always point in north-south direction. If you have a piece of magnet, tie by using a string and hang it from the ceiling, it will always point itself in which direction? North-south direction. That is used to find directions also. Earlier times, the sailors, when they are going for any kind of sail, they always used to have magnetic compass, which was pointing towards north-south direction based upon directive property of the magnets. Magnet also have inductive properties. I should say induction property. What is that, you know? A magnet has a power of making another magnetic material magnetic in nature. Suppose you have a magnet and you have steel pins all around. These steel pins which are attracted towards the magnet will also get some magnetic properties after some time. Why it happens? Because these steel pins are getting induced by magnetism when it is subjected near the magnetic field. So if there is a magnetic substance which is kept near magnetic field for a long time, that magnetic substance also becomes magnetic, like ferromagnetic substances we learned today. If it is a steel kept in magnetic field for a long time, it becomes magnet. So that induction property is also a part of property of magnet. And one more property, anybody can tell me? Monopoles property. That is, monopoles never exist. It never exists. That is, if you break a magnet in two parts, you will still have north-south, north-south. We cannot have only north pole, only south pole. Keep on breaking, keep on breaking, keep on breaking. The smallest part of magnet will also have a north pole and a south pole. So monopoles can never exist. Another important thing about magnet. If you have a magnet, where does this north pole and south pole exist? I told this to you. It is not at the edge of the magnets. Many people think that last is north, last is south. Or some of you think that half is north, half is south. It is not like that. Neither of it is true. Yes, around 85% of the magnet's length is called as magnetic length. And this is called as geometric length. So geometric length and magnetic length are not same. Magnetic length is the exact distance between the north pole and the south pole, and this north pole and the south poles are located little bit inside the edges. How much inside? Around 85%, like how she told, 0.85 times of geometric length is generally the magnetic length. So magnetic length of magnets generally is how much smaller? It is around 85% of the magnet's geometric length, right? The line which joins the north pole and south pole is called as what? It is called as magnetic axis. Magnetic axis. And if I draw a perpendicular line bisecting the magnetic axis, this is called as magnetic equator. Magnetic equator. These are some very basic things everybody should know. What is magnetic equator? What is magnetic axis? What is magnetic length? How much is magnetic length compared to its geometric length? So all these things are very basic properties of magnet, from where the questions will not come in the examination. Just to start with. Now, let us go to the main part of this chapter, this topic, where the questions are going to come from. So now what I'm going to do, I'm going to talk about the Coulomb's law in magnetism. Coulomb's law in magnetism. Any idea about this Coulomb's law? See, Coulomb's law in electrostatics says that the two charges will always attract each other or repel each other by a force which is directly proportional to product of their charges and inversely proportional to square of distance between them. That's how we got Coulomb's law. F proportional to Q1, Q2, F inversely proportional to R square, F proportional to Q1, Q2 by R square, and you got F is equal to mu naught by 4 pi times, 1 by 4 pi epsilon naught times Q1, Q2 by R square. Same way here, we have the force of attraction or repulsion between the poles. What is going to differ here is the constant and the charges. There we use charges, here we will use pole strength. So it will become F is equal to mu naught by 4 pi into Qm1 into Qm2 by R square. Now, what is QM1 and QM2? QM1 and QM2 are the pole strength of the magnet. Don't forget this. Pole strength of the magnet. So the two poles are attracting each other or repelling each other. With what force they are attracting or what force they are repelling is found out by the formula mu naught by 4 pi into QM1 into QM2 by R square. What is the SI unit of pole strength? Any idea? SI unit of QM is what? This question comes in the examination also. It is ampere meter. Remember this. Ampere meter is the SI unit of pole strength. How it comes, you'll understand by the end of today's lecture. So the force of attraction or repulsion between the poles is given by this formula. F is equal to mu naught by 4 pi QM1 QM2 by R square. Electric field is force per unit mass, isn't it? Sorry, charge, force per unit charge. Electric field in first chapter. Same way, magnetic field can be written as this force per unit pole strength. Remember that. When you divide the force between the poles, divide by the pole strength, what you get is called as magnetic field of a bar magnet. So magnetic field of a bar magnet is given by the formula, the force divided by the pole strength of the magnet. Then comes what is a magnetic dipole. Like how you have electric dipole, we also have magnetic dipole. What was electric dipole? Electric dipole was the arrangement of equal and opposite charges having a small separation between them. Am I right? That is, if you have minus q plus q and 2d distance between them, then this arrangement is called as dipole, electric dipole. Same way, if you have a pole QM1, another pole QM2, and a small separation between them, let me name it as 2d, this arrangement is called as magnetic dipole. That is, if you have equal and opposite poles separated by a small distance 2d, then this arrangement is called as magnetic dipole. Remember that. Very similar to electrostatics. There we had minus q plus q 2d. Here we have QM1, QM2, 2d. You can also assume this to be a north pole and this to be a south pole. So equal and opposite poles having a small separation between them forms a magnetic dipole. And same way, like how you had electric dipole moment P is equal to Q into 2D. Here you have magnetic dipole moment which will be given by M. So what is magnetic dipole moment? Also called as magnetic moment, given by M. It is vector quantity. Magnetic moment is given by the formula M vector is equal to QM into 2D, where what is QM? Pole strength. What is 2D? Separation between them. Then how do you define dipole moment? That is magnetic moment. It is defined as pole strength times distance between the poles. Pole strength times distance between the pole is called as magnetic moment. If they ask you what is the SI unit of magnetic moment, QM is in ampere meter, distance is in meter. So ampere meter square is the SI unit of what? Magnetic moment. Remember, this comes in the examination. SI unit of magnetic moment is ampere meter square. Now from here, if you see last 5 years, many times board question has come from this topic. I'll explain you how the questions are coming in the board also. So one more thing I should say you, direction of magnetic moment. Magnetic moment is directed from south pole to north pole. It means south behaves something like negative charge, north behaves like positive charge. Because if you remember the electrostatics, there the electric dipole moment was directed from negative charge to positive charge. Same way here, magnetic dipole moment is directed from south pole to north pole. It's very important. Recently, some schools they wrote exam, SSM school also, question came from magnetic moment. I'll tell you how the questions came and how it comes in the examination. So magnetic moment based questions looks like this. What they will tell, they will say one magnet is there. Okay. And they will say another magnet is kept perpendicular to it. One bar magnet is there. Another bar magnet is kept perpendicular to it with poles lying together. Let it be south pole, north pole. Let this be south pole and north pole of this magnet. And then they will give you the pole strength values. And then they will ask you what is the net magnetic moment of these two magnets. So you should know that South pole, North pole, this is the direction of magnetic moment, M1. South pole, North pole, this is the direction of magnetic moment for M2. So I have one magnetic moment like this, another magnetic moment like this. Then where will the net magnetic moment lie? In this direction, isn't it? And if this is M1 and this is M2, what will be this then? Root of M1 square plus M2 square. Because 2 M1 M2 cos 90 will be 0. It's vectors. A square plus B square plus 2AB cos theta is the resultant vector. And here theta is 90 degree because the angle between them is 90 degree. They are perpendicular. So net magnetic moment will be root of M1 square plus M2 square. One question came last year in some paper I saw. They gave 4 different positions of magnets. Like if the magnet is kept like this, one time magnet is kept like this and like this. One time magnet is kept like this and with some angle 30 degree. And one time the magnet is kept like this, opposite. Which case you will have the maximum magnetic moment? Like the questions are coming. So how will you solve this? You will check if they are in same direction. What is the angle between them? 0. Magnetic moment, if suppose it is south pole, north pole, both are having same south and north together, the net magnetic moment will be M1 plus M2. Isn't it? In this case, it will become M1 plus M2. If both are having same value, it will become 2M. If they gave both the magnets have same magnetic moment, net magnetic moment will be how much? 2M here. Here if it is M and here it is M, suppose the net magnetic moment will be root of M square plus M square. What will be that? Root 2M. Isn't it? Here the angle is 30 degree. This M, this is M. It will become root of M square plus 2M square cos 30. Am I right? Yes or no? What is cos 30? Root 3 by 2. So it will be root of M square plus root 3 by 2. 2 gets cancelled. Root 3M square. Am I right? So now it will be how much? M square plus root 3M square will be how much here? 1 plus 1, 2. 2 plus root 3. So 2 plus root 3 times M. This will come in under root. M will come outside of the root. And here 1 is this direction, 1 is this direction. So root of, that is M minus M. It will become 0. Opposite direction, right? M minus M. It will be 0. So now you check 2, root 2 and root of 2 plus root 3. Which is the biggest? 2. It has the maximum dipole moment. Like that, the questions are coming in the board examination. Are you getting? They will give some position of the magnets and they will expect you to find the net magnetic moment by various positions of magnet. It's a typical question that has come a lot of time in the school and the board examination. So have an idea about it. Today itself, go and see the past year book and solve some questions based upon it. Okay. Then comes, what is the effect of magnetic field on a bar magnet? That is magnetic. One more thing I'll tell you. Whenever you hear the word magnetic dipole, no, what is the meaning of magnetic dipole? When I say magnetic dipole, I said you it is arrangement of 2 equal and opposite poles separated by a small distance. So if I have north pole, if I have south pole, I have a small distance between them. Don't you think it will become a short magnet itself? So whenever you see the word short magnet, it means it is a magnetic dipole. Don't confuse yourself. Short magnet and magnetic dipole, they mean the same. They are the same. Okay. So if you see the word short magnet, it means they're talking about magnetic dipole. Now, same like keeping an electric dipole in the electric field. If you have a magnetic dipole placed in uniform magnetic field, same like that, it will also experience a torque. And there the torque formula was P sin theta. Here torque formula will become equal to B PE, right? So MB sin theta. Let me write like this. So it will become MB sin theta. Where M is the magnetic moment, B is the magnetic field, theta is the angle made between the magnetic moment and the magnetic field. This angle is called as theta. In second chapter, you studied what is the work done in rotating a magnetic dipole in the magnetic field. And you came to know that the work done was U is equal to minus PE cos theta. Here the work done U will become equal to minus MB cos theta. If you remember the second chapter, there are 3 conditions after this. Static equilibrium, neutral equilibrium, and there are three equilibriums, right? One is static equilibrium, one is neutral equilibrium, one is unstable equilibrium. Stable, unstable, neutral. So if theta becomes equal to 0, cos 0 is 1, so u will become equal to minus mb. This is called as stable equilibrium. If theta becomes equal to 90 degree, u will become equal to 0. It is called as neutral equilibrium. If theta becomes equal to 180 degree, u becomes equal to plus mb. This is called as unstable equilibrium. So always remember that a magnetic dipole will be in unstable equilibrium if the angle between the magnetic field and the magnetic dipole is 180 degree. It is in neutral equilibrium if the angle between them is 90 degree and the angle between them is 0 degree, they are in stable equilibrium. This again comes from second chapter only, if you remember second chapter well. So these things are very important once again for the board examination. From here also questions are coming in the board. Then we studied in first chapter what is the electric field due to electric dipole at an axial point, at equatorial point. So same way here also we should know what is the magnetic field due to magnetic dipole at axial point like this or at equatorial point like this. Same like electric field formula. Here the magnetic field at axial point will be how much? Mu naught by 4 pi. There it was how much? If you remember the formula, it was k into, what is the formula? K into 2pr by r square minus d square, the whole square. You remember? So here also it will be 2mr by r square minus d square, the whole square. And there for equatorial point, the electric field was 1 by 4 pi epsilon naught is k into p by r square plus d square power 3 by 2. So here also it will be mu naught by 4 pi into m by r square plus d square power 3 by 2. These things are very important. Never forget this. Magnetic field due to magnetic dipole at an axial point is mu naught by 4 pi into 2mr by r square minus d square the whole square. At equatorial point is mu naught by 4 pi into m by r square plus d square to the power 3 by 2. And if r was much more than d, then we will get b at axial point as how much? R will be much more than d, d will be neglected. So it will become mu naught by 4 pi into 2m by r cube, isn't it? And here you will get, if r is much more than d, b equatorial is equal to mu naught by 4 pi into m by r cube. Do you remember this? See, these things are not only helping you in this chapter, it is also recalling your first and second chapter. The same formula is there. Try to recall. The formula in first chapter was electric field at equatorial point is mu naught by 4 pi into p by r square plus d square power 3 by 2. And here it is mu naught by k into 2 p r by r square minus d square the whole square. Same thing happening here also, replacing p with m and 1 by 4 pi epsilon naught with mu naught by 4 pi. Very clearly visible, if r is much more than d, then b axial is 2 times of b equatorial. Again, similar to that chapter. Somebody is knocking the door? No? Fine. Is it clear to you? Up to here things are fine? I hope it is fine. So if I once again take this, that is, shall I change the page? Yeah, similar something you're writing. Make it fast, please. We don't have much time today. I'll not be able to give time for writing separately. You should keep on writing as I'm teaching only. Done? Okay. Then, apart from all these things, we have one more important concept here. That is called as electrostatic analog. NCERT write it as electrostatic analog. And how I will call it, in the previous chapter, the last topic that we studied, where we studied about moving coil galvanometer. Before that, we studied about what is the behavior of a coil kept in magnetic field. We found tau is equal to NIBA sin theta, where I took NIA as M. I said tau is equal to MB sin theta. I'm talking about that formula now. For torque, we took I into A as M. That is current into area as M. How did we take that? Let us learn that now. Okay. So for that, let us recall the fourth chapter and tell me, for a circular current carrying conductor, pay attention, for circular current carrying conductor at an axial distance, suppose this is R and its diameter is let A. What is the value of magnetic field here? B is equal to mu naught I A square by 2 into A square plus R square power 3 by 2. These things, if you are still not remembering, then it's a very bad thing. So many days have happened. Now you should remember this formula now. This is the magnetic field due to a circular current carrying conductor at an axial distance. At central point, it is mu naught I by 2R. For a straight current carrying conductor, R distance is mu naught I by 2 pi R. And for a circular current carrying conductor, axial distance away is mu naught I A square by 2 into A square plus R square power 3 by 2. If, now please pay attention, if R is much more than A, in this case, R is very big, A can be neglected. If A is neglected, B will become equal to mu naught I A square by 2 into R square power 3 by 2, 2 gets cancelled, 2R cube, isn't it? Do you agree with me? Pay attention to what I'm doing. What I did, I wrote B as mu naught into I A square. I removed this A square as 0. You may say, sir, why cannot take here also A as 0? We cannot take. If a small number is in multiplication, we cannot omit it. Only if a small number is in addition or subtraction, we can omit it. I hope you know this. 1 lakh plus 0.001. 1 lakh minus 0.001 will not affect 1 lakh. But 1 lakh into 0.001 will affect 1 lakh. So whenever a small number is in multiplication or division, then we don't neglect it. We can neglect a very small number only if it is in addition or subtraction. Never forget this, very important. That's why I neglected this A square, not this A square. So if I neglected this, this will become 0. R square power 3 by 2, 2 gets cancelled, will become R cube. So I'm getting B is equal to mu naught I A square by 2 into R cube. Now what I'll do, you see, I'll rearrange the terms. I'm writing mu naught by 4 pi. Okay. Since I divided by 4 pi, I have to multiply by 4 pi. So above I'm writing 4 pi I A square by 2R cube. Are you seeing what I've done? Multiplied and divided by 4 pi. Now 2 will cancel this as 2. So I am going to get mu naught by 4 pi into 2 into I into pi A square will become what? Tell me. Pi into A square. This pi and this A square will become what? Area of the circle. So I can write 2IA divided by R cube. Do you agree with me? So magnetic field due to a circular current carrying conductor at an axial distance, if axial distance is much longer than the radius, is given by the formula mu naught by 4 pi 2IA by R cube. Now, coming back, tell me what is the electric field, electric field due to electric dipole at equatorial point. Sorry, at axial point. At axial point. Just now before some time we did magnetic field. I am asking electric field. Electric field value is E axial is equal to 1 by 4 pi epsilon naught into 2PR by R square minus D square the whole square. This is electric field due to electric dipole at an axial distance. In this case also, if I take R much more than D, then E axial will become equal to 1 by 4 pi epsilon naught into 2 into P, because R 4 will cancel, by R cube, right? Do you agree with me? And here I have got B axial as mu naught by 4 pi into 2 into I into A by R cube. Do you agree? Do you agree? If you compare this equation number 1 and equation number 2, you will get two conclusions from here. One conclusion that you should get is 1 by 4 pi epsilon naught, mu naught by 4 pi, both are constants. 2, R cube. If this is dipole moment, this should also be dipole moment. That is, if it is electric dipole moment, it must be magnetic moment. That's how we get magnetic moment is equal to I into A. Remember that. How magnetic moment became I into A? By the electrostatic analog between the electric field and the magnetic field. It's very important. Moreover, we can conclude one more thing. We can conclude that a circular current carrying conductor behaves like a magnetic dipole. In board exam, question comes for 3 marks. What they'll ask you? They'll ask that, prove that a circular current carrying conductor behaves like a magnetic dipole. What they're asking? They're asking this derivation only. If you do this derivation and prove these two are analogous, then you can write, therefore, this behaves like a magnetic dipole. Magnetic dipole. And it has a magnetic moment of how much? I into A. It means if you have a circular current carrying conductor carrying current I, area is A, then it is behaving like a magnetic dipole which has a magnetic moment of I into A. Current into its area. Is it clear to you? It's one of the most important parts of this chapter. That is, from this chapter, if something is important, then this is very important. Remember that. Okay, I'm talking about this part. If it is clear to you, then we have come to an end of the first part of this chapter. After which, we have to talk about magnetic substances. So, shall I change the page? See, I'm not going to give time for writing because I told you they have to finish a lot of things in this class, but everything is getting recorded. So you can see later if you want to see, that's possible. And what you can write in running notes, you can write. I'm not stopping you from writing today. Generally in my class, I will not give, I will not allow you to write. I'll say, I'm teaching, listen to me, later you write. But in this class, I cannot allow, do that. So you can write along with I am teaching. And if you want to see the video is available. Okay, we're recording it. So I'm going to the next page now. So next in this chapter, we should talk about the magnetic materials or magnetic substances. We will talk about 3 different materials, which are paramagnetic material, diamagnetic material, and ferromagnetic materials. Let us write dia first. Diamagnetic material, paramagnetic material, and ferromagnetic material. Dia, para, ferro. Okay, let us pay attention to these things. So, in simple words, if I say, diamagnetic substances are those substances which does not have lone pair of electrons. And paramagnetic substances or ferromagnetic substances are those substances which are having lone pair of electrons. To understand this, a very basic thing is there. Just now you have learned that if you have a circular current carrying conductor, listen to me very carefully. If you have circular current carrying conductor, it behaves like a magnetic dipole. Am I right? Just now we learned circular current carrying conductor behaves like a magnetic dipole. If you have an electron moving in one direction, it will also behave like current carrying conductor only, because electron creates current. And if there is a current carrying circular loop, it is a magnetic dipole. If it is magnetic dipole, it will have magnetic moment. That's how magnetic properties come inside any substance. So first thing you should understand, whatever you see around yourself, everything in the universe is either diamagnetic or paramagnetic or ferromagnetic. It's not like nothing. It should be, whether it is plastic, whether it is wood, whether it is me, whether it is you, whether it is cloth, whether it is board, whether it is light, everything you are seeing around yourself, no? Every matter can be classified either in paramagnetic category, ferromagnetic category, or diamagnetic category. So, if you remember chemistry, you have this kind of shell filling, right? You have this kind of SPDF shells. You will fill the pairs like this, like this, like this, like this. You feel like this, no? So if you have like this lone pair of electron, see, if you have paired electron, they will cancel each other, opposite spins, clockwise, anti-clockwise, isn't it? If in a particular, what do you call this? Orbital shell, I don't know, whatever you call it. In this box, you have one clockwise or anti-clockwise. If clockwise or anti-clockwise are there, one is north, one is south. Once again, how many of you know this? That clockwise means south pole, anti-clockwise means north pole. So if one thing is moving in south pole direction, that is clockwise direction, one thing is in anti-clockwise direction, they will cancel each other. Net magnetic moment is zero. You may ask me, then how does the diamagnetic substance gets magnetism? That is different talk. I'll talk today now about that. But remember that if you have lone pair of electrons, then it will be categorized in paramagnetic substance or ferromagnetic substance. Because diamagnetic substance have no lone pair of electrons. Remember that. They have only unpaired electrons, that is paired electrons. All the electrons are paired electrons. Whereas diamagnetic substance as well as ferromagnetic substance, what they have? They both have lone pair of electrons. That is, they both have unpaired electrons. Now that makes very clear that if the electron is lone, single electron, it revolves, becomes a magnetic dipole, creates magnetic moment. So it has magnetic properties. Easy to understand that? Single electron creating para or ferromagnetic properties. Difficult to understand is how when I am having paired electrons, magnetic moments are cancelling each other, still I am having diamagnetic nature. To understand this, you should have an idea about electromagnetic induction, which anyhow I am going to teach after this topic, but let me recall once again. Electromagnetic induction is a phenomena whenever there is a change in magnetic flux, there is an induced EMF. Remember this? And Lenz's law says that direction of induced EMF will always be in such a way that it will oppose the cause of it. This is what is Lenz's law. It will be more clear when I talk about that in the next chapter. Okay? So what happens? Imagine, examples I'll tell you. For diamagnetic substances, the examples are any organic substance, any organic things, even water, and even some substance like gold, I guess copper, isn't it? These are, now gold and copper are metals. They have lone pair of electrons. Then also they are diamagnetic. I'll come to that. That is different talk. But understand that how water or how organic things, that is you or me also diamagnetic in nature. We are organic, right? We are diamagnetic. Our food is organic, right? It is diamagnetic. Wood is organic, right? It is diamagnetic. Why is it diamagnetic? Let us understand that first. To understand this diamagnetism shown by these materials, imagine you have a glass of water. I said this experiment to you. In this experiment, what we do, we take a test tube. Inside test tube, we keep some water, and this test tube is put inside a thermocol, and thermocol is kept on the water surface so that it can float easily. Why I am doing all this setup? Because even a feeble magnetic field can be detected. If water is showing magnetism, Even a small magnetism should detect it. That's why I'm creating a condition where I'm keeping a small test tube. Inside test tube, I'm keeping water. This test tube I'm embedding on the thermocol, and thermocol I'm keeping on the water bowl. Now it will move for some time, then come to rest if there is no wind in the room. Now what I do, I bring a magnet near to it. So I have some water. In this thing, I am going to bring a magnet near to it. You know what will happen? This water will be repelled. If water is non-magnetic, why it is repelling? It means it is showing some magnetism. That's how it is repelling. It is repelled by a magnet. Water is repelled by a magnet. Why is it repelling? Let us understand that. So I said you here we have paired electrons. If I zoom it up, we have like this. So one electron moving in clockwise direction, another moving in anti-clockwise direction. Now when you bring a magnet near to it, north pole, south pole, when I am bringing it near to it, what is happening? North is going near to it. It will make this thing as more north because there is a change in magnetic flux. There is an increase in magnetic flux. If there is an increase in magnetic flux, the induced current will reduce it. To reduce it, it must repel it. To repel it, it must become north pole, isn't it? And for it to become north pole, it must have, these both must become a north pole. Initially, they're cancelling each other when there is no magnet. It is, one thing is clockwise, that is south, one anti-clockwise, that is north. They both will cancel each other initially. But when the magnet comes near to it, south also starts becoming north. North will become stronger north. So south will become smaller, north will become more bigger. Now I get a stronger, I got a magnetic dipole here. Because south became small, north became big, it will cancel this south and it will become net north. If it becomes net north, north and north will repel each other. That's why the water is being repelled. So the cause of diamagnetism is what? It is electromagnetic induction. Remember that. If they ask you what is the cause of diamagnetism, answer is electromagnetic induction. These things nobody will tell you in the book. This is just to make you understand how it happens. But the cause of diamagnetism is electromagnetic induction. And just now I told you, diamagnetic materials will weakly repel the applied magnetic field. So it weakly repels the external magnetic field. The external magnetic field. Remember these points. That is, diamagnetism is caused by paired electrons, the elements having paired electrons or a substance having paired electrons. It is shown by organic things, shown by water, gold, copper. It is caused by electromagnetic induction and it weakly repels the external magnetic field. Then comes the paramagnetic substances. What are those? Already know, it is shown by lone pair of electrons. And common sense says that if you have a material which has a lone pair of electron, it will show some magnetism because it will behave like a magnet dipole. Question is, we will not have single electron, right? In an element, we have millions of electrons. And all these lone electrons are not in one direction. They are in different direction. Do you agree with me or not? Randomly oriented. Since they are randomly oriented, net effect is zero. It means if you have a paramagnetic substance, whether it will show magnetism? No. Why? Even though it has lone pairs, all these lone pairs of electrons are not in the same direction. They are in random directions. If they are in random directions, they are cancelling each other and net magnetic moment is still zero. So a paramagnetic substance will not have a net magnetic moment. And since it is not having a net magnetic moment, it does not show any magnetic characteristics until it is subjected to external magnetic field. Because you know that if you have external magnetic field, just before some time I told you that a dipole kept in magnetic field will experience a torque. And torque will align the dipoles, isn't it? Torque means what? It will rotate it. Suppose random direction, it is present randomly. Magnetic field applied, it will align it like this. So the presence of magnetic field will start aligning the dipoles. And if it starts getting aligned, now it will have some magnetic moment. Are you getting my point? This is the logic of paramagnetism. When you have a paramagnetic substance, for example, examples are aluminum, examples are liquid oxygen, liquid nitrogen, isn't it? These are some very good paramagnetic substances. So if I am having liquid oxygen, it will not show any magnetic property. But same liquid oxygen subjected to external magnetic field will start showing magnetic properties. It will start aligning itself. It will start weakly attracting the external magnetic field. The external magnetic field. So, if I talk about paramagnetism is caused by the lone pairs of electrons, because lone pairs of electrons are behaving like a magnetic dipole, creating a magnetic moment. So it shows some magnetism. But an element made up of lone pair of electrons also will not show any magnetic properties, because magnetic dipoles are randomly oriented, making net magnetic moment to be 0. The same substance, when subjected to external magnetic field, the magnetic dipoles will start aligning them in the same direction, creating some magnetic moment. And so it starts weakly attracting the external magnetic field. This property is shown by the materials like aluminum and liquid oxygen. One more question comes very frequently. Question comes like, what is the effect of temperature on paramagnetic substances? You can itself say, see, electrons, even at room temperature, they are very violent. You know this. In 11th, you studied about the kinetic theory of gases. One chapter was there, right? In 11th standard physics. Name itself you forgot. Kinetic theory of gases. In that chapter, one topic was there. Kinetic interpretation of temperature. One topic was there. Remembering topic name at least? Kinetic interpretation of temperature. And in that topic only you came to know that kinetic energy will be 3 kT by m. Boltzmann constant. These things, everything you forgot. Okay. What is the thing is? Temperature creates kinetic energy. Even at room temperature, electrons are moving only, not at rest. You know how it will come at rest? At 0 temperature. 0 means what? Absolute 0. What is absolute 0? You know, minus 273.15 degrees Celsius. If you go to that much low temperature, electrons will stop their movement itself. Otherwise, at room temperature also, it will have some vibration. And imagine if we give more temperature than that. If we start heating a paramagnetic substance, what will happen? Magnetic field also will not be able to align it once again. So the magnetic properties will be lost. It means paramagnetic properties lose its paramagnetic character if subjected to temperature. But diamagnetic substances are unaffected by temperature. So what is the effect of temperature on diamagnetic substances? No effect. What is the effect of temperature of paramagnetic substances? It will reduce the paramagnetic properties. Are you getting my point? So diamagnetic substances are not affected by temperature. Are not affected by temperature. But paramagnetic substances definitely are affected by temperature. Affected by temperature. Remember these things. Question comes from here directly, it comes in the examination. Now comes the ferromagnetic substances, which is very different from paramagnetic and diamagnetic. It is purely based upon something called as domain theory. It is called as domain theory. Now, what is this domain theory? See, in nature, there are only 3 substances, which are iron, nickel, and cobalt. Iron, nickel, and cobalt. These 3 substances are having domains. Now, what is domains? Domains are arrangement of magnetic dipoles in same direction. See, each domain is having different direction, but a particular domain will have same direction of all the magnetic dipoles. Are you able to see this diagram? So these are called as domains. In paramagnetic substances, all the dipoles are randomly oriented. If I have 100 dipoles, all 100 are randomly oriented. If I am having a ferromagnetic substances and if I have 100 dipoles, they will be grouped as 20, 20, 20, 20, 20. And each 20 will have same direction. Are you getting the difference? Here also, if you take a ferromagnetic substances, will it have magnetism? No. Why? Because randomly oriented. If you take iron, will iron be a magnet? No. Why no? Because iron has domains and these domains are aligned in random direction. It will not have any magnetic effect. But same iron, when you are subjecting to what? External magnetic field. Now it is easy for a ferromagnetic substance to align itself, because what will move here? The complete domain itself will move, isn't it? So one domain moving, along with domain movement, the whole dipoles are moving together. So ferromagnetism is stronger than paramagnetism. I hope you get my point. Why ferromagnetism is stronger than paramagnetism? Because in paramagnetism, we have to deal with individual electrons, individual lone electrons. In case of ferromagnetism, we are dealing with domains. So magnetic field is aligning one complete domain, second domain, third domain, fifth domain. Are you getting my point? So it is strongly attracted by the external magnetic field. Strongly attracted. By whom? By external magnetic field. Remember this. Moreover, one more thing I'll tell you. It is found that at very, very high temperatures, remember this also, at very, very high temperatures, a fixed temperature is there called as Curie's temperature. At that temperature, domains are lost. That is, these domains will break and a ferromagnetic substance will turn into paramagnetic substance. These questions are coming in the A and R type questions. A ferromagnetic substance becomes paramagnetic substance at what temperature? Curie's temperature. It's a very high temperature. Once again, if temperature is lowered from Curie's temperature, then it will become ferromagnetic. Are you getting my point? If suppose Curie's temperature is 900 degrees Celsius, suppose, if you are making the temperature as 900 plus, what will happen? It will become paramagnetic. If you are making 800 once again, it will become ferromagnetic. So when the temperature given to a material is more than Curie's temperature, then its ferromagnetic substances are lost, domains are lost, and a ferromagnetic substance becomes paramagnetic substance. But once again, when temperature is lowered from Curie's temperature to normal temperature, once again it turns out to be a ferromagnetic substance. One more question. If you ask me, constant, it is not? In NCERT, they are not given, but it is there. For iron different, nickel different, cobalt different. So 3 different materials will have 3 different Curie's temperature. Okay, it's not same temperature. So I think for iron it is some 900 something. If I don't remember the value exactly. Different materials will have different Curie's temperature. Okay, and if our temperature is more than Curie's temperature, then ferro will become para. Okay, one more thing. I still not told you why copper and gold, even though they are having lone pair of electrons, they are diamagnetic. See, whenever a material is having lone pairs, it also have paired electrons. If you draw this kind of orbital structure, paired, unpaired, right? So whichever element is having unpaired electrons, they are having paired electrons also. Paired electrons are showing diamagnetic characteristics. Lone pair is showing paramagnetic characteristics. So this element, all the paramagnetic elements also have diamagnetic properties. That is why diamagnetism is called as universal. This question has come 3-4 times in the board examination. Which property is universal? Diamagnetic, paramagnetic, ferromagnetic, none of these. Answer is diamagnetic. Why is diamagnetic universal? Because whichever element has lone pair, it also has paired electrons. Paired electrons are going to give you diamagnetic properties. Lone electrons are going to give you paramagnetic properties. Now there is a fight between paramagnetism and diamagnetism. Who wins? The material is that. It means if paramagnetic properties are more than diamagnetic properties, it is overall behaving like a paramagnetic substance. If diamagnetic properties are more than paramagnetic properties, it behaves like a diamagnetic substance. So gold, copper, silver, they are having more diamagnetic properties compared to paramagnetic properties. That is why they are diamagnetic in nature, even though they have lone pair of electrons. But aluminium, liquid oxygen, liquid nitrogen, they have paramagnetic properties more than diamagnetic properties, so they are paramagnetic in nature. Are you getting what I'm trying to say? This is all about dia, para, ferro, theoretical things. Let us talk about the numerical things also. Can I change the page? I will change the page. So now, once again, I was talking about diamagnetic substances, paramagnetic substances, and ferromagnetic substances. Talking about diamagnetic, paramagnetic, and ferromagnetic. Okay. Now, what are these three? What is dia, para, and ferro? Please pay attention. Something very important I'm telling. So, diamagnetic, I told you that here the substance is weakly repelling the applied electric field, a magnetic field. So, the diagram will be like this, isn't it? That is, magnetic field applied is repelled by the magnet. I told you before some time, it is weakly repelling. Repelling whom? External magnetic field. So the diagram will be like this. It comes in the examination. They'll give diagram to you. They'll ask you what material is this, or they'll give the material, ask you to draw the diagram. So this is a diagram of for diamagnetic substances. What about paramagnetic substances? Weakly attracting. So it's like this attraction, but weak attraction. What about ferromagnetic? Strongly attracted, isn't it? We should draw a diagram representing strong attraction by the material. So this is weak repulsion, this is weakly attracted, and what about this? Strongly attracted. Now, talking about the magnetic susceptibility and relative permeability. You know that mu r is equal to 1 plus chi, isn't it? I hope you know this. And you should also know that B is equal to chi times of B naught. You know this. That is, main point is, how much is the magnet substance going to get magnetized? It depends upon the magnetic susceptibility. Okay. So if it is repelling, then magnetic susceptibility must be negative, and small. Why small? Because it is weak. If it is attracted, then magnetic susceptibility must be positive and small. Why small? Because it is weakly attracting. And since it is strongly attracting, magnetic susceptibility must be positive because of attraction and large because of strong attraction. So magnetic susceptibility given by chi B, magnetic susceptibility is negative and small for diamagnetic substance, positive and small for paramagnetic substance, and positive and large for ferromagnetic substance. Whereas the mu r, which is 1 plus chi, will become, see, if you add 1 minus some small number, it will be slightly less than 1. So if mu r is slightly less than 1, then the material is what? Diamagnetic. If mu r is slightly more than 1, it is paramagnetic. If mu r is much more than 1, it is ferromagnetic. Mu r means relative permeability. So relative permeability of diamagnetic substances are slightly less than 1. Relative permeability of paramagnetic substances are slightly more than 1, and relative permeability of ferromagnetic substances are largely more than 1. If they give you 0.995, what is the material? Mu r is 0.995. Para how here? 0.995. Less than 1, right? Diamagnetic. I not told negative. 0.995. Mu r is not negative. Yeah? Mu r is always positive only. It can be less than 1, more than 1, or much more than 1. So if mu r is 0.995, it is diamagnetic. If mu r is 1.02, paramagnetic. If mu r is 2942, paramagnetic. Are you getting my point? If magnetic susceptibility is minus 0.3, diamagnetic. If it is positive 0.5, paramagnetic. If it is positive 25, are you getting my point? If it is negative and small, it is dia. Positive and small, it is para. Positive and large, it is ferro. Again, the question is coming directly from here. They'll give the values to you. They'll ask you what material is that. So that is all about this small chapter. Today I went very slow. Time is almost 1 hour and I have taken only 1 chapter. So definitely I cannot finish all 3 chapters what I planned to finish. No problem in that. I will reduce the portions for you for the coming exam. Okay. If I am able to not take any class, I will not be able to take any class. So I'm feeling like that. So next week, what test you are going to write in the fast track batch will not have all 3 chapters. We'll have only this chapter and EMI. EMI I'm going to start now. Okay. Let us start at least 1 more chapter. Let me cover, which is electromagnetic induction. Fine. Chapter number 6, electromagnetic induction. What, Vaishnav? Any problem? Number 6. Okay. Electromagnetic induction. So this chapter starts with the basic understanding of what is the meaning of the word magnetic flux. Like how you have electric flux, which is defined as the number of electric field lines passing normally through an area. Same way, we have magnetic flux, which is number of magnetic field lines passing normally through an area. Mathematically, like how you have electric flux as EA cos theta, here we will have BA cos theta. So magnetic flux mathematically is given by the formula BA cos theta, where B is magnetic field, A is area vector. And what is area vector? If you have an area, normal drawn on it is called as area vector. Don't think this is area. This is area only. This is area vector. So if I am taking one area and drawing the magnetic field like this, if I ask you, what is the angle between magnetic field and area? You should say not say 90 degree. Because area vector is like this. Magnetic field in the same direction, angle is 0 degree between them. So remember that area vector is perpendicular drawn on a particular area. Never forget that. Okay. So B is the magnetic field, A is the area vector, theta is the angle between magnetic field and area vector. So what will be its SI unit? Magnetic field Tesla, meter square. Tesla meter square is also called as Weber. So SI unit of magnetic flux is Tesla meter square or Weber. Never forget that. Moreover, since magnetic flux is the dot product of magnetic field and area vector, it is a scalar quantity. Never forget this also. They'll ask in exam, magnetic flux is scalar or vector? Answer is scalar. Why is it scalar? Because it is a dot product of what and what? Magnetic field and area vector. Since it is dot product, it must be scalar. I hope you are understanding this. Okay. Then, now comes the Faraday's law. So, after understanding what is the meaning of magnetic flux, Faraday was the person who could find that there is an induced current coming from changing magnetic flux by doing various experiments. The most famous experiments that he conducted was these 3 experiments, where he changed the area, he changed the magnetic field, and then he changed the orientation. When he was changing magnetic field, there was an induced EMF. When he was changing area, there was an induced EMF. When he was changing orientation, there was an induced EMF. It means you can simply say whenever there is a change in magnetic flux, we will have an induced EMF. I'll repeat what he found. By his experiments, he found that whenever magnetic field was changing, there was an induced EMF. Whenever area of the coils are changing, there is an induced EMF. Whenever the orientation of coil was changing, there is an induced EMF. So instead of saying separately magnetic field, area and orientation, these three together becomes magnetic flux. So what did he say in the first law of Faraday? Faraday's first law says that there will be an induced EMF whenever there is a change of flux. So he said that that is whenever there is a change in magnetic flux, there is an induced EMF, which will last only till there is a change in magnetic flux. I'll repeat, whenever there is a change in magnetic flux, there is an induced EMF, and this induced EMF will last only till there is a change in flux. It means if flux is not changing, induced EMF will become zero. Induced EMF will be there only till the point when the magnetic flux is changing. When I'm saying magnetic flux change, it can be magnetic field change, it can be area change, it can be orientation change, it can be anything, but it should change. If nothing is changing, magnetic field constant, area constant, orientation constant, no induced EMF. This was whose statement? Faraday's first law statement. Then comes Faraday's second law. Second law is mathematical part of the same thing. What it says that magnitude of induced EMF is rate of change of magnetic flux. That's all. So first law he gave theoretically. First law he said that whenever there is a change in magnetic flux, there is an induced EMF. In second law he said that magnitude of induced EMF is rate of change of magnetic flux. It means that if you have phi equation given, for example, phi is equal to 5t square plus 3t plus 6, and they ask you at t is equal to 1 second, what is the induced EMF? You can easily find it. How to find it? Differentiate. It will become 10t plus 3, and put t is equal to 1, it will become 13 volts. Isn't it? If you differentiate the magnetic flux with respect to time, you get induced EMF. Put time value, you'll get the answer. That is what Faraday said. Faraday not told about direction of induced EMF. He just talked about magnitude of induced EMF. That's why sometimes if you see in the book, they will put a modulus sign over it. This modulus sign means that Faraday not talked about direction, he just talked about the magnitude. So Faraday gave the magnitude of induced EMF, and he said magnitude of induced EMF is rate of change of magnetic flux. Now, who gave direction? Direction of induced EMF was given by Lenz. So Lenz gave Lenz law. Lenz law is based upon law of conservation of energy. Remember, this comes in the board exam quite often. Lenz law is a consequence of what? Lenz law is a consequence of law of conservation of energy. And what Lenz law says? Lenz law says that direction of induced EMF will be in such a way that it will oppose the cause of it. That is, he added a negative sign in front of it. And negative sign means that the cause of induced EMF is going to oppose it. For example, if I am having a magnetic field, I hope everybody knows it is into the plane magnetic field. In this into the plane magnetic field, if a coil is trying to enter, this coil, when it is entering the magnetic field will try to increase. If the magnetic field is increasing, then obviously magnetic field is changing. If magnetic field is changing, magnetic flux is changing. If magnetic flux is changing, there will be an induced EMF, and it will try to oppose the cause. What is the cause here? Increase in magnetic field. Which increase in magnetic field? Increase in into the plane magnetic field. If you want to reduce into the plane magnetic field, we should have out of the plane magnetic field. To produce out of the plane magnetic field, the current must be anti-clockwise. This cannot be taught in one day. It has to be understood by brain. I have spent a lot of time on this to make you understand it when I was teaching for the first time. Again, I am repeating, it is not something which can be taught overnight. It is very simple understanding. That first step is to understand whether magnetic flux is increasing or decreasing. If it is increasing, try to reduce it. If it is reducing, try to increase it. That is the phenomenon of Lenz law, nothing else. So question comes like, there is a coil here. This coil is trying to exit the magnetic field. What is the direction of induced EMF, induced current? So this coil, if it is trying to exit the magnetic field, then there is a change in magnetic field, increasing or decreasing? Decreasing. Because maximum, if it comes minimum, 0. If magnetic flux is reducing, induced current will try to increase it. Increase what? Increase into the plane magnetic field. To increase into the plane magnetic field, the current must be clockwise, because clockwise will produce into the plane. So the current direction will be clockwise. Are you understanding? That is how we put direction of current. This kind of question is certainly going to come in the examination. Coil is there. Magnet is going inside the coil. North pole, south pole. If it is going to go, then magnetic field is increasing for this coil. If it is increasing, it will try to oppose it. To oppose it, it will become north, repelling. To become north, it must be anti-clockwise, isn't it? It must be anti-clockwise like this. Are you getting my point? Because just now I told anti-clockwise is north, clockwise is south. Why it became anti-clockwise, you're understanding? Because it becomes north pole to repel the magnet coming on it. I hope you're understanding. It's very important for the examination. One question comes, it has come in the board exam also. Coil is there, but it is not connected. If it is not connected, then there is no current on this. How current can be there? Only if it is closed, the current can come. No, open circuit, how current will come? So the answer is no induced current. North pole is passing through it. Whether any induced current? No. But if it is a closed coil, definitely induced current will be there. If it is south pole here, it will become clockwise. Isn't it? One more question comes. What happens to its acceleration? Obviously, acceleration will be decreased. It is opposing it, right? It is coming fastly, it will oppose, so it will become slow. So a magnet passing through a coil will become momentarily slow. Don't think it is very slow. It's going to be slow for a fraction of a second. Once again, when it is crossing down, the same coil, if it is north pole, it is south pole. Now it is going to go down. Magnetic field is reducing. If magnetic field is reducing, coil will try to increase it. To increase it, it will pull it back. To pull it back, it must become south pole. To become south pole, it must have clockwise direction current. This is the basic logic. If somebody wants to learn in detail, go to the video of the class. I have spent 1 hour on teaching the same single topic. More than an hour. Just to teach Lenz law. Today I cannot do that. This is what about the Lenz law. Lenz law questions are like this only, where they will give you some condition and they will ask you to put the direction of current. If you understand the Lenz law, easily you can solve this kind of question. Okay. Then comes in this chapter the concept of motional EMF. Now, what is motional EMF? It is very simple. It says that whenever you have a conductor which is moving in magnetic field, suppose there is a conductor like this, and this conductor is moving in magnetic field, then this conductor will acquire EMF across its end. That is, this conductor, when it is moving, it will be behaving equivalent to a battery. Understanding? Why? How? I have thought about this also. I have told that whenever the coil is moving in the magnetic field, there is force acting on it, because this conductor, conducting rod, right? Rod means it's a conductor, metallic rod I'm talking about. Metallic rod, being a conductor, will have charged particles. If I'm zooming it, if it has charged particles, it will have positive charge and negative charge. So if this positive charge is moving towards right, magnetic field is into the plane, force will act. Magnetic field into the plane, positive moving towards right, it will experience a force in upward direction. Same way, negative will create current in opposite direction, it will be downward direction. So the force, the magnetic force, will make the positive charge to go towards upwards and negative charge to come towards downwards, creating a positive potential here and a negative potential downwards. Are you understanding this? Because all the positive charges are experiencing an upward force, all the negative charges experiencing a downward force. What is going to happen? When this starts, since we are going to have negative and positive polarity, we are going to have electric field coming here. From where to where? From positive to negative. If you see carefully, you'll realize that this positive charge always tries to move in the same direction of electric field. So magnetic field was pushing upwards. Electric field is pushing downwards. What will happen? There will be an equilibrium when both FB and FE become same. At that equilibrium, no further charge will move. Positive, negative will stabilize. And then FB is equal to QVB, FE is equal to QE, QQ gets cancelled, velocity into magnetic field is equal to electric field. Electric field is also equal to electric potential by length. So I get electric potential EMF is equal to B into V into L. This EMF is called as motional EMF, BLV or BVL. B is the magnetic field, V is the velocity, L is the length of the conductor. This is the length of the conductor. So whenever you multiply magnetic field with velocity, with its length, you get what is the potential going to develop across the ends of a conductor. It means that if I am connecting some rails here, and suppose some resistance here, and suppose a battery, a bulb here, this bulb will glow if I am moving the rod right or left. Because if I am moving the bulb right or left, induced EMF will come. This EMF will create current. Current will glow the bulb. Not some high power bulb, small 0.5 watt bulb. I hope you get my point. So motional EMF concept is B into V into L, magnetic field into velocity into length. Next in this chapter, we have learned about self-induction and mutual induction. What is the meaning of the word self-induction? Self-induction means in the coil where the magnetic flux is changing, in the same coil induction comes. And what is the meaning of mutual induction? There will be two coils, primary coil and secondary coil. Change of flux in primary coil will produce induced current in secondary coil. Let us understand this. So suppose I am having a coil like this and connecting a battery here and a key here. Whenever I am putting the key on, current is increasing from 0 to maximum. If current is increasing, magnetic field is increasing. If magnetic field is increasing, magnetic flux is increasing. If magnetic flux is increasing, there is an induced EMF, which will try to oppose the cause of it. Cause is increasing current. It will try to reduce it. Same way, when I am turning it off, now current is reducing from maximum to 0. Current reducing, magnetic field reducing, magnetic field reducing, magnetic flux reducing, magnetic flux reducing, induced current will try to increase it. Once again, it is opposing the cause. So the bulb, suppose I am having a bulb here. After I off, no, bulb will not directly off. It will flicker and off. This flickering of bulb will happen because of induced current. It offs, on offs within fraction of a second. Why it is after offing, why it on once again? Induced current came, passed through it, on it. Once again it went, it offed. The flickering of bulb happens because of induced current. Are you getting? So in this case, in which coil I am having the change in the flux, in the same coil I am having the induction also. This phenomena is called as self-induction. And since phi is equal to Li, I can say L is called as self-inductance or coefficient of self-induction. L will become equal to phi by I. And one more thing from here, you can write L also equal to minus E by di by dt. All these things I have derived in the class, how it came. So remember, self-inductance or coefficient of self-induction is defined as magnetic flux per unit current, which will be Weber per ampere. Weber per ampere is also called as Henry, Henry, Henry. It is also defined as opposing EMF per unit rate of change of current. So whether I say flux per unit current or I say opposing EMF per unit rate of change of current, both are same. This is self-induction. Same way, if you have a coil and if you connect a battery here and you have another coil which is having some galvanometer here, when I am owning it, flux is changing. That flux is linking with this flux also, this coil also. This is called as primary coil. This is called as secondary coil. So whenever there is a change in primary coil, it affects the secondary coil also. That kind of induction is called as mutual induction. So here phi will become equal to phi in secondary coil will become M into current in primary coil. So M will become equal to phi S by IP, same unit Henry. And how we define it? Flux in secondary coil per unit current in primary coil. Moreover, M will be given by minus ES by dIP by dt. So how do you define mutual inductance? It is opposing EMF in secondary coil per unit rate of change of current in primary coil. Very important question comes directly from here. Definition of mutual inductance or definition of self-inductance. Self-inductance is defined as opposing EMF per unit rate of change of current, opposing EMF in secondary coil per unit rate of change of current in primary coil. After that, in this chapter, we have the self-inductance of a long solenoid, which you should derive. That is, when you have a solenoid like this and you connect it with source of power, then what is the self-inductance of this coil? L. If you derive, you will get the answer as mu naught N square A by L. Never forget this. Where N is the number of turns, A is the area of coil, L is the length of the coil. This derivation I have done in the class. Go through the notes. It's very important for the examination. Next is mutual inductance of two long solenoids. What is that? If you have one solenoid like this, primary, another like this, secondary, and if you are finding what is the mutual inductance between them, then it will come as mu naught N1 N2 A by L. So self-inductance of a long solenoid is mu naught N square A by L. Mutual inductance of two long solenoids is mu naught N1 N2 A by L. Both these derivations I have done in the regular class. Go through the notes if you want to go through the notes, because again, it's time-taking topic. But final result is this only. Okay. Last topic in this chapter is methods of generating induced EMF. Methods of generating induced EMF. So you know that induced EMF is equal to minus d phi by dt, isn't it? After using Lenz's law. And what is phi? You know by now, phi is B A cos. If theta I can write omega t. If BA comes outside, minus BA, what is d by dt of cos omega t? D by dt of cos omega t will become minus sin omega t. So E will become, omega also will come, plus it will become BA omega sin omega t. So from here, for n turns, I will have induced EMF is equal to N B A omega sin omega t. Is it clear to you? Induced EMF will be N B A omega sin omega t, where N is number of turns, B is magnetic field, A is area of coil, omega is angular velocity or angular frequency, and sin omega t is the phase of the coil. From here only we get AC generator. What is that? If you have a magnet here North Pole, if you have magnet here South Pole, and if you keep the coil in various positions, that is when the theta is 0 degree, 90 degree, 180 degree, 270 degree, 360 degree, put here the values of omega t. Sin 0, 0. Sin 90, 1. Then sin 180, 0. Sin 270, minus 1. Sin 360, 0. You will get a sine wave like this, isn't it? So this NBA omega is called as E naught. That's how we get E is equal to E naught sin omega t, where what is E naught? E naught is NBA omega. This is called as peak EMF. peak EMF E naught is NBA, omega n is number of turns, B is magnetic field, A is area of coil, omega is angular velocity. So this formula gives you what is the equation of induced EMF. And if you keep a coil and rotate like this, when theta is 0, E will be 0. When theta is 90, E will be E naught. When theta is 180, E will be 0. When theta is 270, E will be minus E naught. When theta is 360, E will be once again 0. 0 plus 1, 0, minus 1, 0, which will make a sine graph. That's why we say that induced EMF is alternating EMF. And that's how we come to alternating current chapter, which I'll take in the next class. This week, coming week test, you will have only magnetism and matter and electromagnetic induction. There is no alternating current. We will see that topic in the next class. Till then, take care. Bye-bye. We'll meet again in the next class.
Thank you.
Thank you, sir.
Take care, take care, take care. Oh.